Alright, so we'll start with the sine. Just from our unit circle, I know that when x is 0, the sine of 0 is 0. And when x is pi halves, the sine of pi halves is up at 1. When x is pi, the sine of pi is back to 0. When x is 3 pi halves, the sine value is negative 1. And then when x is 2 pi, the sine value, sine of 2 pi is 0. And so when we connect those, we get that. And so that is our parent function, and we're going to move around that parent function the same way we move around any function. So if I put a 3 out in front, that is a vertical stretch, and it's going to multiply all the y values by 3. So the ones that are at 0 are going to stay at 0, but one's going to become 3, that's going to become negative 3, and so that idea that it gets stretched by 3 is nothing new, but we're going to call it the amplitude. So we have fancy names for everything. We have an amplitude of 3. And so that's that. What if we put the 3 on the inside? So what if we had y equals the sine of 3x in there? That's going to affect the x's. It's going to be a horizontal shrink, and it's essentially going to divide all the x's by 3. It looks like you're multiplying, but when it's grouped in like this, you undo it. So what we like to do here is that normally what we call the period, this graph finishes in 2 pi. So a normal sine graph, the period is 2 pi. But for this new one that we're doing, when you've got this shift, the x values are getting divided by 3, so the period is being, I'm making hand gestures that you can't see, the period is being shrunk. So the period that was normally 2 pi is being divided by that number, we call that b, and so my new period is 2 pi over 3. So, and the amplitude is still a 1. So when I go to graph this, an easy way to graph these is I know I'm going to finish a full cycle in 2 pi thirds. And I can get, the graph is kind of divided up into kind of 4 important points, right? It goes up and then down and then up in the middle and down in the middle. And so if I just kind of slice this, if I end at 2 pi thirds, in the middle I'm going to be at half of that, at pi thirds. And in the middle of that, if I divide pi thirds by 2, I get pi 6. So my increments are pi 6. So it's 1 pi 6, 2 pi 6, 3 pi 6, 4 pi 6 will be kind of the 4 important parts of my graph. So when I graph, my sine starts at the origin, starts at the middle, and then it's going to have a high point at 1, and then back to the middle, a low point at negative 1, and back to the middle, and you can draw that curve. Yay! So we'll do another one like that. So like let's say you had y equals the sine of 5x, then that would affect the period. So the period, the new period is going to be 2 pi over b, so 2 pi over 5. So when I go to graph, I know I'm going to finish a full cycle at 2 pi fifths. And I could find the middle by taking half of 2 pi fifths. And I could find the middle of that, half of pi fifths is pi tenths. And then that's my increment. So it's 1 pi tenths, 2 pi tenths, 3 pi tenths, 4 pi tenths. And those are the 4 important points. My amplitude was a 1, so I'm going to go up 1 and down 1. And sine starts in the middle, so it starts in the middle, it goes up, then back to the middle, then down, then back to the middle, and there's my lovely sine graph. Cool. Excellent. So there's other places you could put the coefficients. So what if I had like y equals the sine of x and I put the 3 out there? That just does a normal vertical shift. It goes up 3. So when I go to graph this, my new center line is at 3. So sometimes I like to draw a dotted line at 3, and that's where the x-axis used to be. It's just everything's hiked up here. And since the amplitude is still a 1, because that's just a 1, the highest point is going to be 4, the lowest point is going to be 2, and it's going to bounce between those. Since my period is just a normal 2 pi once around the circle, I could get those normal points that I got in the beginning by taking that 2 pi, dividing that by 2, dividing that by 2, and then it's 1 pi halves, 2 pi halves, 3 pi halves, 2 pi. Sine starts in the middle, and then it goes up, and then back to the middle, and then down, and then back to the middle, and there it goes. Excellent. What else can we do with sine? So we could make it negative. So if I had the same graph and it was just y equals negative sine of x plus 3, then it would be the same thing, except instead of going up first, it would go down and then back to the middle and then up and then back to the middle, and it would reflect just like your normal reflections, right? This was positive x squared, this was negative x squared. We've got those reflections there. So I'm going to bank this, make sure it's recording okay, and then I'll be back. So let's do the same thing with the cosine graph. So now when you take the cosine of 0, you know the cosine of 0 from your unit circle is 1. And that's why cosine starts in the up position versus in the middle like sine. When you take the cosine of pi halves, that's 0. The cosine of pi is negative 1. The cosine of 3 pi halves is back to 0. And the cosine of 2 pi is 1. So when you connect the graphs, don't let it lose its curves. It's got the same curviness as sine, and it looks like that. And of course it goes on forever, but this is just one period. So you can do all the same shifts that we did with sine. So I'll jazz some up. So what if I had like the 2 and a cosine of, I don't know, 6x or something like that. So now we have an amplitude of 2, and we have a period of 2 pi over b, so 2 pi over 6, so just pi thirds. And so when I go to graph, it'll finish a full cycle in pi thirds. Half of that is pi 6, half of that is pi 12ths, and then it's 1 pi 12ths, 2 pi 12ths, 3 pi 12ths here. You can reduce it to pi fourths at any time, but it's easy to keep them unsimplified for a while you work with them. So it's got an amplitude of 2, so the highest is going to be is 2, the lowest is going to be a negative 2. And since it's cosine, it starts up. So it's up, and then middle, and then down, and then middle, and then up. And then you just draw your cosine. Check. And if it were that same thing but negative, it would just start down, and then middle, and then up, and then middle, and then down. And just don't let it lose its curves. So cool. We'll do one more for good measure. What if you were graphing y equals 3 times the cosine of 2x minus 4? So now you're down 4, so your new kind of middle line is at negative 4. Your amplitude is 3, and so from the negative 4 I would go up 3, so my highest point is going to be at 1, and then my lowest point down 3 is at -7. So I'm going to be bouncing between -1, 4, and -7. My new period is 2 pi over 2, so that's just pi. So I'll finish a full cycle in pi. Half of that is pi halves, half of that is pi fourths, 1 pi fourths, 2 pi fourths, 3 pi fourths. And cosine, when I go to graph, cosine starts in the up position, and then it goes back to the middle, always back to the middle, then down, then back to the middle, then up. And there you go. Check. So now that we know how to do sine and cosine, secant and cosecant are actually the same exact thing. If you know how to graph sine and cosine, you can graph secant and cosecant. The reason for it is because, let's do cosecant first. Cosecant is 1 over sine. So wherever sine blows up, wherever sine is 0, cosecant blows up. So if I were to graph a very light sketch of my normal sine, so I graph, so up, middle, down, middle. So there's sine, and when I go to graph cosine, cosecant, everywhere that sine is trying to be 0, cosecant is undefined, and that's where your little asymptotes come from. And then 1 over 1 is just 1. And then 1 over a very small number is a very big number. 1 over a very small number is a very big number. So that's why you get those weird looking parabola type deals bouncing off the bumps of your sine graph. So now we can go back to the beginning, and anywhere we drew a sine graph, we could draw the equivalent cosecant graph. So what if, let's see, if they had asked us to draw y equals cosecant of 3x, I would have started with drawing the sine graph, just like I did. And then any place that the sine was 0, I would draw in asymptotes. And then I would bounce off the bumps of my sine graph. So you just draw the normal, like swap out cosecant for sine, deal with the period, the amplitude, all that normal stuff, and then draw the asymptotes and bounce off the bumps. So same deal with this one. If I wanted y equals the cosecant of 5x, I would draw the asymptotes where the sine was 0, and I would bounce off the bumps of that. If I wanted to draw y equals the cosecant of x plus 3, then I would draw the sine of x plus 3 like we did, and then anywhere it reaches those middle points is where the cosecant blows up. So it's not necessarily the x-intercepts when it gets shifted, but those middle points would make it die, or make it undefined, and then you bounce off the bumps of that. So, and then we can do the same idea with secant, because if you have a secant, that's 1 over cosine. So if you're ever graphing a secant graph, you just take your normal cosine graph and do the same idea. So now it's 0 there and there. You've got those asymptotes, and you get this weird little half parabola. There's like another half over here, but if you're just drawing one period, you've just got that strange sort of half guy. Full bump there, another little half guy there. Of course, it does keep going, but we don't always draw it if we're just drawing one cycle. So same deal if I wanted to do, let's do, oops, that was a 2 there. If I wanted to graph y equals 2 secant of 6x, I would graph 2 cosine of 6x just like we did and bounce off the bumps of that. And so the green part is my graph. Make sure on your test, when you draw your kind of scaffolding cosine function, you either draw it really light or dotted so she knows that it's not part of your actual graph. So yeah, so that's secant, sine, cosine, secant, and cosecant. The other ones are tangent and cotangent. They're a little bit more annoying because they've got a couple little quirks. So if you graph tangent, you know that the tangent to 0 from your unit circle is 0. I'm going to graph the tangent of pi fourths. I know is 1. And I know that the tangent of pi halves is sine over cosine there. It's undefined. So I'm going to go on the other side, see what happens if I do the tangent to negative pi halves. From my circle, I know that's negative 1. And then it's undefined at negative pi halves. So when I plot it, a normal tangent function looks something like that. So notice the normal period for tangent from negative pi halves to pi halves, its period is pi, not the normal 2 pi. So that's just slightly annoying. The other thing slightly annoying about tangent is that half of it's on one side and half of it's on the other, so joy. But we have the same stretches and shrinks that we do for sine and cosine. So if I threw like a 3 out in front, that would be a vertical stretch by 3. There is no amplitude, but it still kind of helps to think of the 3 as multiplying the y values by 3. So that's not going to change, but the 1 is now going to be up at 3, so it gets stretched, and the negative 1 is down at negative 3. So it's just this skinny guy there. Check. And then if I want to graph y equals 3, if I put the 3 on the inside, if I do y equals tangent of 3x, my new period is not 2 pi over b anymore, just a pi over b. So pi over 3. And for tangent, what I have to do is divide that by 2. So it's pi 6 on either side. So half of the period is over here, half of the period is over here, and that's where my asymptotes are. And then in the middle it goes through 0. If you want in the middle of that at pi 12ths, it'll be up at an amplitude of just 1 and down there, and there's that. Cool. Let's see. So if we did it again, like let's say you had y equals 2, actually let's do 3 tangents. I haven't done any with the fractions there yet, I keep forgetting. 1/2. So here the period would be pi over a half, so it ends up being 2 pi. We're going to split that in half, so it's going to be pi on either side. So on one side I'll have pi, on the other side I'll have negative pi, and that's where the asymptotes go. Tangent goes through the origin, and my quote-unquote amplitude is 3. There is no amplitude, but it helps to know that in the middle I'll be 3 up and 3 down, so it's a stretched out graph. If they had like a negative out front, you could just flip it upside down. Check. If they added stuff on the end, you could just move it up and down or right and left. Or actually, I haven't moved right and left yet. Moving right and left is a bit more annoying. I'll do that later. You didn't do too much of it, I don't think. Okay, so let's talk about cotangent then, just to finish them all. And cotangent, I'm not going to bounce off a tangent. I'm just going to kind of do it. It's kind of nice in the sense that the cotangent of 0 is undefined, so your first asymptote is right on the axis. the cotangent of pi fourths is 1. The cotangent of pi halves is 0. The cotangent of 3 pi fourths is -1. I can draw a straight line. And the cotangent of pi is undefined again. So now, here's your normal cotangent, and it's falling down, right? So normal cotangent falls down like so. The period for the normal cotangent is pi, just like tangent. So we can do all our normal stuff. We're getting kind of used to it now. Let's say we had y equals a half times the cotangent of, what if I had a pi x? Then my period would be just pi over b. So pi over pi is 1. And so I'm going to finish one full cycle in 1. And so that's where the last asymptote's going to go, and the first asymptote goes there. It'll cross through the middle at the halfway point, so at half. And then halfway through that, it'll be up at the amplitude of a half. And then in the middle, I'll be down at an amplitude of a half. And then normal cotangent falls down. And there that is. Cool. What else haven't I done? So, I talked a little bit about shifting. So what if you had, I think for what you've done so far, you haven't shifted that much. So what if you had like sine of x plus pi halves? That goes to the left pi halves. And we call that a phase shift. So horizontal shifts are called phase shifts, just because they like to make everything sound more scary than it is. So all you would do is you would take that normal sine graph we drew earlier and then shift it all to the left pi halves. So remember, we finished at 2 pi. And so this point would shift to negative pi halves. This point would now be at 0. This point would move there. This point move there. That point move there. You could even subtract pi halves from all the original x values. And get it that way. Okay. So I think that's okay. I'm going to stop it there.